Okay, I think we're ready to get started. Everyone. All right, so we're very happy to have Johanna Erdmenger, who's going to tell us about berry phase factorization and wormholes in AdS CFT.
Yes, thank you very much. It's a great pleasure to be here, and I'm very happy to tell you about some work of our group in Würzburg. And I'm very grateful to my class, many of whom are actually in the room. So first of all, there's Annalena, who's sitting there. She's been very much involved in this, and Renee, who's sitting over there, and Giuseppe, where's Giuseppe? Giuseppe is there. Okay, so I owe quite a lot of this very nice work to them. Okay, so let me see. So this is one of the castles in Würzburg, just to give you some appetite to visit at some point. Let me give you an overview of what I'm going to tell you. So let's say the first 2/3 of the talk I'm going to devote to wormholes and factorization in AdS CFT. And I'm going to focus on two different cases, the first of which is berry phases in quantum mechanics, so in 0+1 dimensional systems. And then I move and show you some very nice relations between the geometry and entanglement relation that happens here to the case in 1 dimension higher, which is 2-dimensional CFTs and their gravity dual. And so the last third of the talk, I'm going to talk about something slightly different, which is discrete holography, which we've also been working on quite a bit about recently. Okay, let me start with the berry phases for wormholes. And okay, so as everybody at this workshop knows, wormholes provide a relation between entanglement and geometry in AdS CFT. And so our starting point was this very nice paper by Hermann Verlind from last year, who showed that the concept of a wormhole in some particular sense relating to geometry and symplectic forms is also present in very simple mechanical models. And in particular, what we're going to use is that the berry phase that I'm going to define for you provides a geometrical understanding of how the degrees of freedom entangle and what the different spaces can be characterized from a geometric point of view. So we can use this to describe the factorization puzzle, and we can also do this in 1 dimension higher than in quantum mechanics. Okay, so the first part of the talk about entanglement in berry phases will be based on these two papers. The first one is about quantum mechanics, where we actually collaborated with two colleagues, Flavio Noguera and Jeroen van den Brink, who are condensed matter physicists within this joint initiative of German science funding, where we ended up with lots of condensed matter physicists, and so they are also, so we are also part of this joint initiative, and so there was some incentive to work with our collaborators there. And then the second part, this is going to be much more mathematical. We will study berry phases in AdS3 CFT2. Okay, so let me start with the quantum mechanics case. Let me give you a very brief reminder about the geometry that we're going to consider. So we consider an eternal AdS black hole, which I guess is very familiar to everybody here. And so it's important to note that we will this type of wormhole is non-traversable, but there will be some geometric concept that will be super important and will show up in almost every slide that I'm going to mention, that there's actually a singularity in the time coordinate at the horizon, because the time-like killing vector switches sign there, which creates a singular geometry. And this singularity will play an important role. There's some wind, but okay, if you're not disturbing wind, I think it's fine. Okay, so as Juan Maldacena already introduced a very long time ago now, one can view this eternal black hole in AdS spacetime to be dual to two copies of the boundary CFT on each side. And actually these two copies are entangled in a TFD state, which I think is also very familiar to everybody in this room. And I've written down here for completeness. And so that very naturally to the ERS EPR proposal, according to which two entangled CFTs with EPR correlation are connected through a wormhole or an Einstein-Rosen bridge. Okay, so a more recent development, also I think Dan Harder was quite involved in this, is the so-called factorization puzzle. So the two CFTs on the two sides have disjoint Hilbert spaces, since there's no interaction between them. And so we have this factored structure between the left and right Hilbert space. However, the wormhole in the middle is a semi-classical object, and so it should have just one Hilbert space, which does not factorize. And then obviously there's an apparent contradiction, and what you see is that the Berry phases give a very nice interpretation of this apparent contradiction. So as I mentioned, the starting point is this work by Hermann Verlinde from last year, where he considered wormhole-like structures in very simple quantum mechanical models. The point is as follows. Consider the partition function for a thermal system, a thermal quantum mechanical system. Now, writing this as a path integral in phase space, which is, so the phase space is composed of generalized coordinates of momenta capital X. And if you remember classical mechanics, these phase spaces are naturally equipped with a symplectic form that takes this form here. Then using this, the path integral can be written in this form, where there's one term which is an integral over the symplectic form over this disk geometry. So the circle here at the boundary is the essentially temperature. Okay, so your compactified time. And so this is the disk geometry which enters the integral here. And then there's a boundary term just over the thermal circle, which is HDT. Now, if the symplectic structure is exact, which means that you can write it as an exterior derivative or something else, then you can use Stokes' theorem and it changes to this. And then actually you have factorization, and so you just have to integrate over these circles. However, if the symplectic structure is non-exact, you cannot do this. And this means that your integration region becomes something connected, like here you see for the case of if you have 4 of these partition functions correlated here. And so this integration region then very naturally leads to these wormhole-like structures. Okay, so that's the starting point. We can use the Berry phase to characterize this behavior very nicely. And so I'm going to show this interacting 2-qubit system in quantum mechanics. And essentially what we're going to see is that states with the same entanglement, in the sense of the same entanglement entropy, may still have different Berry phases. And that will be mathematically described by a non-exact symplectic form, which also very naturally leads to non-factorization, as I've just explained for the wormholes. And so because we collaborated with the condensed matter colleagues, one nice feature is that this behavior can actually be characterized experimentally. So that's what we realized in what we proposed in our paper. Okay, a very quick reminder of what the Berry phase is in quantum mechanics. So the starting point is the time-dependent Schrödinger equation, where we look at some ground state that you can write in this way with a basis in time, a unitary time involution. Then the Berry connection is defined as the derivative with respect to this set of parameters. So that gives the dimension of this connection. And inserting this into the Schrödinger equation gives you this equation for this unitary matrix. And then the Berry phase is defined here. Okay, so this is the path integral, the path ordered integral along exponential along in this parameter space. One spin-a-half particle in a magnetic field, then essentially you get a structure like this, and you get a closed curve in the space of the magnetic field. And so it's not in real space, it's in the space spanned by the magnetic field. And actually the space has a singularity here. And again, singularity will play an important role because it leads to this non-exact symplectic form. So this is a picture. Very nice lectures by David Tong, which I recommend for this. Okay, so now let's look at the case where we combine this Berry phase with entanglement. So we will look at two in an external magnetic field. For instance, describing the electronic Zeeman interaction in a hydrogen atom with a proton and an electron. And so the Hamiltonian that we start with is this very simple Hamiltonian where we have two coupled spins with coupling J. And one of the spins actually also interacts with a magnetic field. And we choose it in such a way that the one magnetic field is parallel to one of these spin operators S1. Now there's a couple of unitary transformations that are possible and which preserve the entanglement entropy of the states. For instance, we can generalize the second term in this Hamiltonian to the full scalar product and consider unitary transformations just acting on S1, which return this term to this original term where they are parallel to each other. And so these transformations just acting on the first spin will be of the structure here with two different patches for the north and south pole of the SU2 sphere. And the second spin, we can choose unitary transformations as we wish because it doesn't interact with this magnetic field directly. So we perform a unitary transformation, which is made as a tensor product, one of which acting on the first spin and the other acting on the second. And the second we choose to be of this form with some parameter lambda between 0 and 1. This parameter lambda should not be confused with that parameter. Here, these are the parameters of the module. This is spanning our path, but this is now just another free parameter, and the path is actually spanned by these thetas and phi. Okay. So the ground state written in this singlet and triplet language looks as follows, where this angle alpha is determined in terms of the constants in the model, so the magnetic field and the coupling. And then you can actually show, I mean, this is relatively straightforward, but still you have to be a little careful because the trace is only taking over one of the two spins. The entanglement entropy does not change when applying these unitary transformations that act on the spins individually. And then we can calculate the Berry phase in a slightly more mathematical setting, which we'll also later use in the CFT2. So we define the Maurer-Cartan form, which is a connection on a group manifold defined for any group element sigma. So this is our Maurer-Cartan form. And from this, we can calculate the Berry connection, which is the ground state expectation value of this Maurer-Cartan form, which looks like this. And now we insert just out the simple model that I presented before, and then the result is going to be this. So it depends. Alpha is the constant J and B essentially in the Hamiltonian. Theta and phi are our geometric variables. And then you can actually see that if you calculate now the Berry curvature, that it will be non-zero. So the Berry curvature of the so-called Kirillov constant symplectic form, which is the exterior derivative of this Maurer-Cartan form. And then the Berry phase takes this form here. And so you can see that lambda is equal to 1, it will actually be non-zero. Okay, so here it's again, so it's non-trivial as long as this parameter is not equal to 1. And so the two transformations must be different. And you can actually trace back this fact that the Berry phase is non-trivial since this Kirillov constant form is not globally exact. Okay, so this is our symplectic form, which in this case is proportional to the volume form of this S2. And so we see that there's a non-exact form here. And so we have two states, we have the same entanglement entropy, but different Berry phase. Okay, and now there's a very nice geometrical statement that we can make here, and which will come back later when I talk about 83 CFT2. So the projective Hilbert space is in fact CP3. So it's the space if you put together these two spins, each of them individually have CP1. And so the projective Hilbert space is then SU4 in total, quotiented by U3 because there's a number of phases which don't play a role. And so the original two qubit spaces are CP1, so, sorry, original CP1 structure, which is embedded here. And now if you don't have entanglement, then the ground state lies in this CP1 times CP1 space and describes local one-sided properties. However, you can show when you have maximal entanglement that the states are non-diagonally embedded in the submanifold of CP3. And so the statement is that the maximally entangled orbit is a Lagrangian submanifold of the entire CP3 space. Okay, so written in mathematical language, what you can say is that we have one spin and the other spin, and there was in CP1, which is SU2 over U1. And now you can already see this non-factorization happening in this very simple example, because when you combine things together and look at this maximal state, it sweeps out a so-called orbit, which where both of the SU2s are kind of fibered or quotiented by the same U1. Okay, so and that leads to this non-factorization, which we then want, yeah, question. Yeah, yeah.
I'm a little bit confused. What's this under the orbit?
Sorry, what is?
The orbit. What's the flow under which this orbit is formed? Oh, yeah, okay, so yeah,
Yeah.
okay. Maybe my confusion is I don't understand this mapping. Like.
Yeah, I will give a lot of explanation for the orbit for the CFT2 case, but here, I mean, essentially, I'm just starting from this U1, okay.
Okay.
From the SU2 transformations for each of the two spins. I will define orbits in a second for the CFT2, but it's a good question. But here I think it's extremely simple. I mean, you have one left-handed spin, one right-handed spin, which you can rotate, and then you just say it's fibered over the same, or over the same fiber. I mean, especially for one, when you rotate the one with the plus sign, you have to rotate the other one with a minus sign, due to this, the fact that you have two patches on your group manifold. Yeah, there's another question there.
I think I'm confused about something more basic. So I thought the factorization problem was about how gravity factorizes, but you seem to be explaining how quantum mechanics doesn't factorize. Am I misinterpreting what you're saying?
I'm only at the beginning of my talk. I mean, I think I'm saying it's, I'm doing quantum mechanics and I see a manifold which doesn't factorize. Okay, so that's what I wanted to show. Okay, but there will be, I will move to CFT2 case in a second. But okay, so the statement is that we have a two quantum mechanics system with two CFTs that are entangled, but in fact, this orbit actually leads to a non-factorized manifold.
This manifold,
yeah.
Is this the manifold of maximally entangled state?
Yes. Yeah. Yeah. Yes, exactly. Yes, correct. That's what I'm saying. So, I mean, I think it's interesting from the point of view of the non-factorization puzzle that indeed in a very simple quantum mechanics systems where you need the interaction, I mean, without the interaction, and you need the magnetic field to characterize this Berry phase. So we see some non-factorization happening. So the manifold of, exactly as Dan just said, the manifold of maximally entangled state is not factorized. I think that's very interesting from the point of view of non-factorization theorem, okay, or a factorization puzzle. Okay, I don't want to spend too much time now about this, but one nice feature about this very simple quantum mechanical model is that it might be possible to investigate the structure actually experimentally. And so by using the so-called quantum tomography, which allows you to measure full density matrices, and they can measure products of Pauli matrices like this, for instance, and then determine the phase of states. And then the idea would be to have a simultaneous measurement of the Berry phase with respect to this external magnetic field and of the entanglement by measuring the quantum mechanical phase in this single and triplet states to look at the relation between both and see that if you have states with the same entanglement, they have nevertheless a different Berry phase. Okay, and so here are some proposals where how this could be done. And I mean, I think it's interesting that this is something very basic in quantum mechanics, which could actually be amenable to a measurement. Okay, so we are trying to convince people to measure this. Okay, so now let's redo the whole thing in one dimension higher. So going back to this paper, in particular with Annalena, who's sitting there. and René, of course. And so now let's do the same for CFT2, which is holographically dual to AdS3 series. Okay, and then here the group that we are going to consider is the Virasoro group, which we write as the diffeomorphisms of the circle. So the group elements include these diffeomorphisms, which depend on an angle phi, which parameterizes this S1, and there is the central charge. Okay, so then we have the standard Virasoro generators. And now there's a different behavior whether we look at the vacuum or highest weight state labeled by H. So this is invariant under L1, L-1, L0, and L1. So this has an SL2R symmetry. As a general highest weight state is just invariant under L0 and has a U1 symmetry, which is then the stabilizer group. And so we have the left and right moving sectors. So for the vacuum, these two sectors have these symmetries, and for highest weight states, we have those two factored symmetries. Okay. Now, because we want to look at the holographic dual as well, let me just mention a few facts about holographic renormalization for AdS3. So denoting the boundary matrix by Gij0, the bulk spacetime is completely fixed in the following way. So if we have an expectation value of the energy momentum tensor of this form, then actually the Pfefferman-Graham expansion in AdS3 terminates after this term. And we can actually calculate the second and fourth order term in this way. And okay, so the symmetries are as follows. So if we, for the highest weight state, which is invariant under U1, or the other, the vacuum, which is invariant under SL2R, this becomes killing symmetry of the bulk. So in particular, for CFT in the vacuum, the expectation value just gives us the central charge. And so this corresponds to an SL2R symmetry. And so this is dual to the SL2R symmetry of empty AdS. Okay, now let me tell you co-adjoint orbits of one example, which we already saw in a simple quantum mechanical case. So here I'm talking about a gate, which is arises there in the context of maybe people here also work on complexity, so they know what a gate is. But this is just an element of the algebra that we consider. And then this is the definition of an adjoint transformation of this group element here. And the co-adjoint transformation on a state V is defined by this relation here. And now what's a co-adjoint orbit? So a co-adjoint orbit is a set of states V that is reachable through co-adjoint transformations of this type on a fixed state V0. And for the Virasoro group, this co-adjoint orbit is actually a Werner module. So okay, that's we pick one representative of this orbit, and then by this co-adjoint transformation, we can recover the entire orbit. And so again, there's a relation to phase spaces. So we can view this orbit as being a phase space, and this means we can again associate a Hamiltonian to it. Now, this co-adjoint orbit is naturally associated with a symplectic form again, written here. And according to this phase space interpretation, we can actually define a so-called geometric action, which then corresponds to this Hamiltonian that I just mentioned on this co-adjoint orbit. And this action is just the integral over the symplectic form. Okay, now this is general formalism, and now we apply it to the Virasoro group. And then so we pick a function f out of the dysmorphisms of the circle with a central charge. And then the orbit is obtained by this co-adjoint action on this representative. And then you can actually do the calculation for the Virasoro algebra, and then this is what you get. So this is your transformation, the representative, and there's a Schwarzschild derivative of your different. Okay, so now this formalism of Berry phases that I explained for this very simple quantum mechanical model also works in this more complicated case. And for the case without entanglement, so when you just have one AdS CFT with just one boundary, okay, so in the standard Poincaré patch coordinates, this was done in this very nice paper by Oblak, which I very much recommend. And So now here the Berry phase is generated by diffeomorphisms that change the CFT state. And now we can do this exact same formalism with the Maurer-Cartan form as I introduced in the quantum mechanical model, so which is done here. And we have to include the central extension. And so if we do run the entire formalism, then the connection gives rise to a Berry phase as before. And now this associated Virasoro Berry phase probes the geometry of a particular coadjoint orbit. So the coadjoint orbit is this square. So if we move around a circle there, then if we go outside the orbit and apply the same transformation that takes us around the circle, then we go around the spiral, okay? And this difference here is then a phase which leads to this Berry phase. Okay, so I'm just saying that this quantum mechanical concept is very naturally generalized to a CFT2. Okay, now, and we can obtain the gravity dual of this because we note that for the stress tensor, the stress tensor is an element of the dual D algebra, as written here. And so then we obtain the dual bulk geometry associated to these Virasoro coadjoint orbits from the Barnianos geometry. And okay, so essentially that's the metric that we have. And these functions which are here, they're obtained from the expectation values of the energy momentum tensor. Okay. And these concepts, they can now be very nicely applied to two-sided geometries as we need for a wormhole. So here actually we use this very nice paper of Eno and collaborators who already investigated the geometric structure of an eternal AdS black hole in AdS3 with two boundaries. So that's a picture from their paper. And now if you look through one throat of the wormhole towards the other, then that's what you see. And then you can very naturally define a holonomy by going around the other end of the wormhole. And so this is the holonomy that you get. Now, these authors, they first considered very simple U1 Chern-Simons action in AdS3, which is written here, and also just the abelian case. And then for Chern-Simons actions, the boundary values of the fields, written in this way, they define a boundary action. Now we have two boundaries, so there's a capital psi on the left-hand side and the capital psi on the other side, and this holonomy also enters very crucially. And so this is the action from their paper. So the boundary action for this Chern-Simons theory looks like this. And okay, I don't want to go into too many detail what it's actually entering here, but very crucially, there's this holonomy contributes to this action. An important role again, because now we see, I mean, I already showed this for the quantum mechanical model, and now we see a very, very similar structure here. So we can look at the conjugate momentum and the symplectic form for the phase space associated with this model. So, and we can in particular define a conjugate momentum for the holonomy in this way. And then we get the symplectic form on the boundary phase space. And there again, you can show that it's non-exact due to the contribution of this holonomy. And so essentially, so this means loop group. So here we have this Westermino-Witten or Katsuguri symmetry for the Westermino-Witten model. And mathematically, exactly the same happens as I was indicating before. So then due to the presence of this holonomy, the space is not factorized because again, we have just quotient, so there's a common quotient for the two left and right-handed sides of the wormhole. Okay, so it's mathematically very similar to what I explained before. Okay, that was just for this very simple U1 model, but now you can do the same for the Virasoro symmetry. So for SL2R times SL2R. So, and so the symmetry transformation now changed the states in the CFT. And the symplectic form on the phase space can be mapped to the symplectic form of the Virasoro group manifold with a coupling between both CFTs. Okay, so, and then again, we see the same pattern that I'm advocating. So, and again, the possibility of having this mathematical structure relies on having a symplectic form.
Thanks. Yeah, so previously when you wrote an equation like that, we understood it as the manifold of maximally entangled states. So what's it the manifold of now?
Looking at these orbits of the Virasoro symmetry. So I just picked some particular representative, like the vacuum or some highest rate state. And then I calculate the orbit in this mathematical machinery that I introduced to you on the previous slide.
Yeah, but I mean, are you just doing group theory, or is this supposed to be some statement about the CFT Hilbert space or the Hilbert space of the bulk gravity, or it's really just statements about?
Okay, I think at the moment I would say it's a statement about, okay, I'm making a statement about the boundary. So going back to this Trans-Simons example, maybe. And so I think in the Virasoro case, it's a similar thing. So this is an action involves the boundary values of the gauge fields, so of the bulk fields. It's an action for the boundary values of the bulk fields. Yeah. And for this, we get this factorization. It's true that I didn't say anything about the elementary fields in the boundary CFT.
So these are these are sources. I mean,
yeah, the sources. Yeah, exactly.
Sources,
this is a statement for the sources of the boundary CFT.
So you're making some statement about the manifold of possible boundary sources.
Yes.
If I understand correctly.
Exactly.
And so the but you're doing you're doing some kind of quotient, right? In principle, there are lots of boundary sources, right? So.
Yeah, okay, but I mean, we know that our CFT has to have the symmetry. So,
so maybe just the stress tensor?
Yeah, we're looking at the stress tensor, yeah.
So usually I would have thought a source for the stress tensor is a boundary metric.
Well, okay, so this is the Trans-Simons case.
Right.
Here, I'm not sure if did I write all the details? Yeah, okay, maybe let me come to, I'm explaining it here probably.
Okay, I think I get a sense of where.
You got it?
Roughly.
Okay, maybe let me explain this and then okay. So actually what we can do is to use a reparameterization of these boundary values of the fields. And then what we get is that we get a geometric action on each of these boundaries, which corresponds to the orbits of the stress tensor manifold. Yeah, exactly. And the coupling comes from the fact that I have one action on the left and one action on the right, but they are forced to have the same holonomy. I mean, there's a contribution in this action which involves this B0, and the statement is that left and right has to have the same B0. Okay, so the connection via the bulk forces me to have the same B0, which is this one, and it's related to the stress tensor of the CFT. Okay. So the asymptotic dynamics of this BTC black hole is described by the coupled Virasoro Berry phases. And so both sides are coupled by the holonomy, and so there's actually a radial Wilson line connecting them. And so again, there's non-factorization. So essentially, from the field theory point of view, you can say that, okay, I have one geometric action for the orbit of the stress tensor on the left-hand side and one on the right-hand side. And the fact that they're related via AdS CFT means that this B0 has to be the same in both of them. And that's related to the holonomy of this non-exact symplectic form. Okay, that's one type of Berry phase that you can look at in these AdS spaces, but there are actually other types of Berry phases, one of which we call the gauge Berry phase. And so that's more in line with these Brown-Renaud transformations. So now in the presence of a black hole in the middle, you cannot define them globally anymore. You can just define them locally near the boundary. And so that leads to another type of Berry phase. And what is very important here is that there is no global killing vector in the presence of a wormhole, and that again leads to a non-exact symplectic form. So looking at this figure here means that it makes a big difference whether you evolve with the sum of the two Hamiltonians on each side, so assuming that you have the TFD state on each side, or if you evolve with the difference, okay, because this is a symmetry which does not transform the state, but this one does. And then essentially, again, what happens for the case, so the first line here is for the case on the left, the second line is for the case on the right. For the case on the left, we get a non-zero Berry connection just by inserting the expression for the TFD state. And for the other case, remember that time goes up on one side and down on the other. It's a symmetry, and then this Berry connection actually just vanishes. Okay, so for this transformation here, we actually get a non-vanishing connection. Maybe I should, so you can also do this calculation very nicely in JT gravity explicitly. You can write down the phase space of, so there you have a Hamiltonian, you can write down the phase space, and you can also calculate the Berry phase, and it exactly matches this picture of the TFD state. Okay, and finally, I'm just going to mention this because Bartek is also here. So another possibility that one can use is the modular Berry phase. So that's a slightly different scenario than I showed before because it has to do with finite intervals. Okay, so Bartek suggested this for one side, and so the new thing is that we again did it for a two-sided wormhole object. So the idea here is to consider an interval on a constant time slice in the CFT with a reduced density matrix rho A, which is dual to a bulk region bounded by an RT geodesic. And then the idea is to consider a modular Hamiltonian for this reduced density matrix, which generates an abstract time evolution with respect to the modular time parameter. And so the choice of the modular time is I gave for each interval. And then again, the parallel transport of the interval around a closed loop leads to a Berry. And so just very briefly, so we applied this to the wormhole with a two-sided scenario. These authors, Hartmann and colleagues, they already observed a transition in entanglement, and also see now a change in the Berry curvature. So in the phase where this is the RT surface, we have a non-zero Berry phase, but then there's a transition. You go to lower temperatures where the two RT surfaces decouple, and then again, in that case, the Berry phase then vanishes. Okay, so and as I promised for the last, say, 15 minutes of my talk, I'm going to change gears a little bit and talk about something a little different, which is discrete holography. Okay, so and I'm briefly going to introduce you to these two papers that we also wrote in Würzburg with a number of colleagues. So in particular here, there's my colleague Harry Henriksen, who is a statistical physics physicist. And then again, there's Giuseppe, who is here, and also our student Pablo Bastero and René. Okay. Okay, so the idea is to establish the AdS CFT correspondence after discretizing the hyperbolic space. Okay, so then first one has to explain why would this be an interesting thing to do. Well, okay, that's the program is to find a kind of new version of the AdS CFT correspondence, or say gauge gravity duality, where you don't have continuous variables and so don't have a continuous quantum field theory. However, I would like to mention that there's many other areas of theoretical physics that people are very interested in this, and so let me just talk you through this. So in particular, within condensed matter physics and even electrical engineering, just this one paper, or as a typo there, sorry, by this group of people, but they're also with other collaborators. They have many other papers before. So Ronny Tonomal is our condensed matter colleague in Würzburg. They actually studied Hubbard models on these hyperbolic lattices. And then on one other direction of interest is from lattice gauge theory. So there's lattice gauge theorists like Richard Brouwers and who actually perform a lattice gauge theory analysis of these type of hyperbolic lattices. And also within AdS CFT, there's this very nice story of the periodic AdS CFT correspondence, which was first proposed by Steve Gupta. And then there's a lot of connection to this tensor network, space-time reconstruction. So, and also mathematicians are interested in this. So there's this very nice recent paper by Mathilde Marcolli and collaborators. And then from the point of view of quantum information, space-time reconstruction by Isat and Alexander Jan, who's also sitting here somewhere. So there's a lot of interest from different sides. So what's the goal for us as the holographers? Well, is to establish really both on the bulk and boundary theories and demonstrate the dualities in this configuration. And so, okay, so the hard point is to actually find a Hamiltonian for this boundary theory. Okay, let me tell you a little bit about these lattices. I should say there's a lot of very beautiful mathematics about these lattices, and so which ways to be made use of. And so usually these tilings, they're labeled by two letters P and Q. So, and P, this pair is the so-called Schläfli symbol, and this symbol means that there's Q regular p-gons that meet at each vertex. Okay, so this is 5, 4. So we have what's the name of a polygon with 5 corners in English? A pentagon. Okay, sorry. God, yeah. So this is a pentagon, and you have 4 pentagons, and this is a heptagon, and there's 3 heptagons, and well, this is a hexagon, and 4 of them meet. Okay, very good. So, and you can actually show that the tile. This gives you a tiling. Well, obviously, if you have hexagons and 3 of them meet, then you get just a plane, but if this relation is satisfied, then you get a hyperbolic space. Okay, so we realized in the course of this is that if we just work in AdS2, Euclidean AdS2, then if you take the limit of infinite, so obviously this is a non-compact space, so there will be infinitely many of these polygons, and so if you do it in Euclidean AdS2, then the area, the boundary manifold will just be an S1, a sphere. There's actually a mathematical theorem proving this. Whereas if you do this in AdS3, then you get a fractal at the boundary. Okay, so that could be very interesting by itself, but it makes your life hard, even more hard. Okay. So let's stick with AdS2 for now, because then we can make use of this nice fact that we have the S1. Okay, so the simplest thing we thought would be to check what happens to the Brightman-Friedman bound if you look at such a tessellation. And actually, you see something interesting happening here already, even before you put your tiling, just by cutting off at a finite distance from the boundary. Okay, I mean, if you do numerics on these lattices, you always have to cut off the finite distance from the boundary. So then the question is, so here you see your usual Brightman-Friedman bound, and you see the global AdS metric on a constant time slice. So in Euclidean AdS2, this is the equation of motion for a scalar. The boundary behavior is the usual story that you do in AdS CFT. But now the thing is that we cut off at a finite boundary value. Okay, so if we write this global coordinates here, then epsilon shows up here, and epsilon goes to 0, then we reach the boundary. So now, since we're in AdS2, the Brightman-Friedman bound is at -1/4, which is here. But now, if you actually solve this differential equation of this manifold with a cutoff due to this finite geometry, so normally in continuum language, you would think that below this bound, everything is unstable. So here we're plotting always the value of the field in the middle, okay, in the middle of your anti-de Sitter space, away from the boundary. But so if you have a large cutoff, then there's still some regular values and just the occasional singularities. But then if you decrease the value of the cutoff, they become much more dense. And then in the limit, when epsilon goes to 0, it would fill up below the Brightman-Friedman bound. And now the interesting thing is that this almost doesn't depend on the values of P and Q when you put this tessellation. So here, this is a numerical plot now. So these black squares is what I showed you on the previous slide. Okay, so here, this is the cutoff. This is the point of where, so this umklapp point is this first point where you see a singularity when you come from positive values of m squared and then come down here. And so then you see if you make your epsilon smaller and smaller, you approach the continuum value of the Brandner-Friedman bound. And now if you start doing this for lots of different tessellations numerically, lie almost on the same curve. And okay, so the numerics breaks down at some value, but then asymptotically they all lie on this line of the continuum case. This is a continuum case with a finite cutoff, okay, and then you take the cutoff to 0.
Sorry.
And yeah, question?
What are you computing on this, on the y-axis?
On the y-axis is the position of the first singularity below the actual continuum Brandner-Friedman bound.
And how does this depend on how you're tiling it?
Yeah, that's just the point. It doesn't depend. This picture,
Right.
Okay, this is an
Right. So I guess my question is, for a particular tiling,
Yeah.
How do you compute this?
Well, you just numerically compute. You numerically solve this differential equation on a lattice. Okay, let me spare you the details of how to numerically. It's a numerical calculation where you only solve on this particular.
I see. There's a discrete tiling-based version of this that you solve.
Yes. Okay. Yeah. You take those tilings and you numerically solve this differential equation on this lattice. Yeah. Thank you. Good question. So and the key result is if you do it for AdS2, due to this fact that asymptotically you just have an S1, that you almost see no dependence. And so these lattice gauge theory groups that I mentioned, the calculated correlation functions at the boundary, and these also, the dimension also does not depend on P and Q in this simple case. And that's supposed to change when you go to AdS3, because then you have a fractal at the boundary. Okay, so and then things become much more hard. So yeah.
The battery is...
Yeah.
Okay. Are you working in Euclidean signature? Or
yes.
So time is also discrete in some sense?
Well, okay. I was super short. Okay. So at the moment, the only thing that we do is that we're working in Euclidean AdS on a constant time slice.
That's what I thought. So then time,
yeah.
But to solve the wave equation, don't you have to solve it in the time direction? Shouldn't there be time derivative?
Well, you can just solve this equation in Euclidean space. That's not a problem. But of course, you're absolutely right. The question is, can we do the same thing in, say, AdS2 + 1? And then the numerics gets quite involved. But our numerical colleagues, they're working on this right now to include the time.
Well, when you solve it just on the hyperbolic disk, which Brandner-Friedman bound do you use? The AdS3 one? Or
no, the AdS2 one. Okay, good point. Okay. So -1/4 is the one for AdS2.
So then you're really you're really in AdS2 now.
Yes. Yeah. Okay. We could have said, let's forget about time. Just consider AdS2 Euclidean signature. Full stop. But okay. So the only point I want to make. It's not totally inconceivable to add a time direction, but of course that makes the numerics a lot harder. Yeah. Okay, yeah, but we're working on that. Yeah, thanks. Yeah, sorry for confusing you. Okay, let's just say Euclidean space. Okay, and the nice thing is that you can now put your Brandner-Friedman bound on this hyperbolic tiling. You can realize this as an electric circuit, and the idea would be that some electrical engineers can build an anti-de Sitter space, and they should see particular resonances according to this Brandner-Friedman bound. Okay, sounds good. Okay. So you can just use Kirchhoff's laws. Okay, so the things that you learn in first year as undergraduate to realize this bound as on a hyperbolic tiling, and so what we found is that you need a lot of coils and a few capacitors. And so to really experimentally realize this is going to be hard because these coils, they're going to talk to each other. There will be non-local couplings, and then of course, okay, I'm not sure how easy this is, but okay, in calculations you can do what you like, and so this is a numerical simulation. So if you sit at this first singularity, then if you have a small drive, then you see that your system starts fluctuation quite wildly. But if you don't sit at this singularity, then it dies off again after a while. Okay, so that's kind of cute thing to do. I'm not sure that's going to revolutionize anything in electrical engineering. Okay, it's fun. Good. And very finally, let me briefly mention this paper where the idea is that we progress of really defining Hamiltonians both in the bulk and the boundary. And so here's a proposal which is just a beginning because it doesn't fully do all the things you would like a duality to do, but nevertheless has some nice features. So in analogy to the standard gauge gravity duality, we would like a theory on the discrete geometry of this PQ tiling. Again, let's stick to Euclidean case for simplicity for now, and then have some Hamiltonian at the boundary. And so here's the way of defining a Hamiltonian here at the boundary of the discrete space. Okay, so what we use are so-called inflation rules. And so that's just the way of creating your hyperbolic lattice shown here in two different examples. So you start with a central tile and then construct concentric layers of tiles going out. And well, then you stop at the finite value for now. And okay, so there's a particular rule that if you have a node with two internal neighbors, you assign it with letter A. And then just looking at this tiling here, then if you have, so these blue dots also belong to the same tiling. Okay, I should, if you zoom in a little more into my figure, then you see that they have three internal neighbors. And then if you inflate and you go to the next layer and the next layer, then you have to replace these letters by a sequence of these letters. And okay, in view of the time, let me not talk you through exactly how this all works. Here it's a bit simpler to see. So you have an A is the red dot, and then, if I'm not mistaken, then in the next line you have a blue, a red, a blue, a red, a blue that are connected to this. That gives you this B, A, B, A, B. Okay. Yeah.
So far, this seems sort of theory independent.
Sorry, that depends.
Theory independent, like.
Yes. Wait till the next slide. Actually, that's completely theory independent, and the problem is that we don't know the action in the bulk is. But okay, that's just what I want to say is this procedure, even if you don't have a Hamiltonian in the bulk, leads to a prescription of constructing a Hamiltonian at the boundary. And that's nice because I mean, there's a lot of work on bulk reconstruction, also in this context of tensor networks and so on, but it's never quite clear what is actually your Hamiltonian at the boundary. And here there's a possibility of defining one. And the interesting thing is that this tiling itself defines the sequence of the couplings. And so if you do this now n times, this rule that I just presented, then you get an aperiodic spin train, okay, and this generates a pattern. So this is now a view of the boundary after a finite number of steps. And so then what you do is that every edge you assign with a spin a half particle. That's for no reason except that it's known how to calculate with these things. And I agree, it's maybe not the best thing to do to use a spin a half variable, but okay, let's do it because there's already quite a lot of work on this. And then every vertex gives you a bond, and every letter gives you a coupling. Okay, so these A's and B's, they give now couplings J, A, J, B between these spins. Okay, and then in this way you generate an aperiodic spin chain that's well known in the literature. And now there's relevant marginal and irrelevant deformation. So in the irrelevant case, the model has the same critical properties as the homogeneous one. But of course, the most interesting one is to get a relevant deformation. Okay, and then we looked at an XXZ spin chain that you generate in this way. And okay, here we have a Hamiltonian at the boundary. I know there's some degree of arbitrariness because nothing motivates to look at spin-and-a-half particles, but nevertheless, let's use the existing literature where these models are actually very well established. And in particular, if we take this coupling to be 1 and we have the XXX chain, there's actually some very interesting stuff just happening here in this RG flow case. So the idea will be that we start in the bulk with a hyperbolic tiling, which of course is something kinematical. I mean, it's not associated with any dynamics, but then we use this inflation rule and we get an aperiodic sequence at the boundary. Then for this, we can very well motivate at least a particular choice of Hamiltonian, which is this aperiodic XXX model. And then we can use tensor network techniques. So this, this order renormalization group to reconstruct the bulk, okay? And it's nice because it's the discrete nature of the bulk is reflected in the nature of the couplings at the boundaries. That's a cool feature, but so we are not quite yet there because only an arrow with dots because the tensor network for our case is not quite started with yet. Okay, so this is what we're working on now, is to really implement the symmetries, and there's some guidance from people who work networks who already looked at this. But then I fully agree with what you just said. Later, we would also need a Hamiltonian on the bulk, and then the idea would be to look at maybe some dynamical triangulation for gravity, and so that would be the idea. There's a lot of work on dynamical triangulations, but none of them is in hyperbolic space. Okay, so that would be a motivation to do this, and then the idea would be to construct this. Of course, if it takes spin-and-a-half, it automatically means that we don't have a large n limit. Okay, so where's the large n limit in all of this? This is another open question that we need to address. Okay, in view of the time, okay, let me just quickly say that, okay, you could say, well, this is totally ad hoc, but at least we have some motivation why this is a good idea, because we can actually, it's possible to calculate the entanglement entropy in this XXX chain. And actually, so it's piecewise linear, but there's an envelope. So this is the number of sides of the boundary you get by your inflation rule. And you do get an envelope of a logarithmic behavior, and you can calculate the coefficient of this behavior, which is actually, if you want, an effective central charge. But now in this case, that strongly depends on P and Q. And then we only were able to calculate it for some special cases. For instance, this one when P is equal to 6 and Q is larger than 4, then you get this coefficient here. Okay, so but it's already reassuring that you get a logarithm. And then you can just very naively compare by looking now at the Ryo-Takayanagi formula in this discretized bulk and find different ways depending on your tiling how to define the shortest geodesic. And then just using the standard RT formula and identifying the coefficient as a central charge, we also get a central charge that is a function of P and Q. Of course, this function of P and Q and from what we get from this aperiodic spin chain, okay. But of course, there was no reason to believe that they should be the same. But at least it gives something to work from. Yes, I know. That's why I'm going to start with my conclusions. Okay, just flash the conclusion. So we talked through this in 10 seconds. So I talked a lot about non-factorization and relating this to these non-exact symplectic forms and the Berry phases. And I showed you this mathematical structure being present in quantum mechanics and in CFT, which gives a nice new way to characterize this relation between entanglement and geometry. And there's even these nice relations to possible experiments that you could do with these spins, entangled spins. And then I talked very briefly about discrete holography, about realizing the bright lunar figment on hyperbolic tilings. And we have this first proposal for a boundary Hamiltonian from the inflation rules. Okay, thank you very much.